A chi-squared test for independence is used when we have two categorical variables and we're looking to tell if they're related somehow. That is there an interaction between these variables, meaning they're dependent, or is there absolutely no association or relation between them, meaning they're independent? Chi-squared tests for independence are going to rely on a contingency table, which means our very first step before we even do the test is to go ahead and find what are called our expected values. There'll be a separate video explaining how we do that. We find the expected values because it turns out we have some assumptions we need to meet in order to be able to even run a chi-squared test for independence. The first assumption is what we call the 10% rule. And that is, when we look at our sample, it can be at most 10% of our actual population. So that is, we have a restriction on how big our sample can be. It can't be like 20 or 15% of the population. At max, it can be 10% of the population. Another assumption we have, where this limits how big it is a restriction on how small it can be. That is, we need our expected count to be at least 5. Now, there's a little bit of a caveat to this, and that is, it's okay for maybe 1 or 2 of our expected counts to be under 5. At most, 20% can be under 5. So that is, if you think about a contingency table that has 4 cells on it, we can't have any of those cells under 5 because 1 out of 4 would be 25%. So once again, we're hoping all of our expected counts to be at least 5, at most 20% under 5. Now, if we meet those assumptions, we can go ahead and start our test. The first step to our test is to list, and we'll list R, which is the number of rows in our table, and C, which is the number of columns in our total. These do not include totals. So that is only where the data is. I use these to calculate degrees of freedom, and degrees of freedom for chi-squared test for independence is C-1 times R-1. After I've calculated my degrees of freedom, the next step is to go ahead and find my hypothesis. My null hypothesis is that my variables are independent. That is, I'm going in running on this idea that there's no relationship between them. I'm trying to prove the opposite, that is, I'm trying to prove they're dependent. After I've listed and come up with my hypothesis, the next step is to go ahead and find my test statistic. Just like a chi-squared test for goodness of fit, my test statistic is chi-squared, and that is sigma, or the summation of my observed minus my expected squared all over my expected values. So once again, sigma adding up, my observed minus expected, I square them so that they don't cancel each other out, and divide by my expected to find the ratio, or the relative deviation. After I find chi-squared, the next step is to find my p-value. And the fifth step is my conclusion. My conclusion fits the same basic model all of my hypothesis tests have. That is, I compare my p-value to 0.05. If my p-value is less than 0.05, I will reject H0. What that means in this hypothesis test is I'm rejecting the idea that these are independent. If I'm rejecting the idea that they're independent, that means there is enough evidence to say they're dependent. That is, I'm saying that, in fact, my variables are somehow related to each other. The other option is if my p-value is greater than 0.05. This would mean I fail to reject H0. What this is telling me is there is not enough evidence to suggest they're dependent. And we need to be careful here, because what I'm saying is there's not enough evidence to suggest they're dependent. This means they may be independent. In no way do I claim for sure they're independent. I say, okay, can't prove they're dependent, maybe they're independent. This outlines my 5 steps for my chi-squared test for independence, as well as the assumptions I need to make so that my test works out. In this video, we're going to be talking about how we calculate our expected values for a chi-squared test for independence. The first step we take is we actually copy over the contingency table we're going to be using. This table on the top left corner here is from the first example on your follow along worksheet, and it looks at whether or not severe reactions in children is related to where they receive a vaccine or a shot. That is thigh and arm, and yes or no for a severe reaction. I'm going to start by copying the table over. So yes and no, thigh and arm, and then as always, my last column and last row is always my total. What I do next is I copy over the totals, and that's it. I can't change the fact that this study looked at 13,810 children. I can't change the fact that 8,992 of them had an injection in the arm. Same up here. And my totals down here as well. So I keep my group totals. Now, to figure out where I'm going from here, I need to remember that my null hypothesis in a chi-squared test for independence is that my variables are in fact independent. And if I'm assuming things are independent, I can think back to my probability, which tells me that the probability of A and B is equal, if these two are independent, to the probability of A times the probability of B. This is really nifty because it allows me to do things like say, okay, I want the probability that yes, a child has a severe reaction, and that their injection was in the thigh. Well, if these are independent, this is the same as the probability that yes, they have a severe reaction times the probability they have an injection in the thigh. I could find these values here based on my table. So the probability yes, a kid has severe reactions is 106 over 13,810. Once again, tracing that yes all the way down. And chances they have a thigh injection would be 4,818 over 13,810, tracing the row across. And what this would give me then is a probability that, yeah, a kid had a severe reaction and that their injection was in the thigh. Now, what I actually want to find in this specific instance is not this, but rather what goes right here. That is, I don't want the probability a kid has this happen. I want the number of kids that have this happen. Now, if I asked you what 10% was, you could find 10% of my sample size by taking 10% times the total, right? 10% of 13,810, which means if I give you this as a percentage measurement, you could find out how many kids fit in that category by taking that thing right there and multiplying it by 13,810, right? That is, if this is the percent who fit in this category, this will give me the number who fit in it. And that's because I'm taking a percentage times the overall total. Now we could actually calculate that, or we could look at this a little bit more in depth, and that is pulling it over on the side here. I notice I would have 106 over 13,810 times 4,818 over 13,810. And then if I want the number of people, I'd multiply that by 13,810. So again, this is the percent of people. And this right here is the total. So if I take the percent times the total, I'll get the number of people who fit in that category. Now I can actually simplify this algebra, and that is, you notice how I have a 13,810 at the end here? I can use that to cancel one of these, which means, in reality, this number right here, I could find it by taking 106 times 4,818, all divided by 13,810. Or if I'm going to go ahead and round, 36.98 to 2 decimal places. Now I want to be clear here that I calculated this by once again taking the probability times the probability times the overall total, but because we want to be able to do this for any contingency table, we should probably find a simpler way to do it. And the way we're going to do this is we're going to look at the individual parts here. So let's look at this 107 first. Sorry, 106. That 106 corresponded to the 106 here, and we used it because it was the total number of kids who, yes, had a severe reaction. That is, that 106 was my column total. So I have 106, which is my column total, and I multiply it by this 4,818, and that 4,818 came from over here, and what that corresponds to is actually my row total. So on the top, I have my column total times my row total. Now on the bottom, I ended up with this 13,810. And that 13,810 came from right here, which is my overall total. Or my sample size, if you'd prefer. This over here then gives me my formula to find any expected value on a contingency table for a chi-squared goodness of fit. Once I've got this number, notice I could repeat it for the rest of the cells, or I could just use the fact that it's additive. That is, to find this cell right here, I could just take 4818, the row total, minus 36.98 to find that one. I could then use subtraction and addition to find the rest of these. Now that we've got a formula, let's go ahead and practice using that formula. For our next example, we're going to refer to the second problem on the worksheet, and that is we're looking at whether or not rape victims seeking medical attention after their attack is related to their income level. Now, our null hypothesis on these is always we're assuming independence, as we're assuming that a woman is equally likely to seek medical attention regardless of her income level. To test that, we're doing a chi-squared goodness of fit, and the first step before we do anything is always to find our expected values, because once again, we want our expected values to be over 5. When I find my expected values, I copy over my table and I leave the center blank. I only keep the totals. After I've copied my table over, I go ahead and select a cell to start with. I'm going to start with this one right here. And to find it, I go ahead and I take my row total times my column total divided by my overall total. In this case, this will be row total of 49 times column total of 124 divided by overall total of 226. Normally when we do these, we'll go ahead and we'll round it to 2 decimal places. Because this is our first full example, I'm going to go ahead and round to the nearest whole number. When I do that, I get 27. So that'll be 27 right here. Notice right off the bat that what actually happened is there were 30 women in that category, according to my top table. So right away I see there's a difference between what I'd expect if they were independent on the lower table and what I actually got with my data. However, a difference of 3 people doesn't seem like a large one. What we'll do next is we'll go ahead and fill in other numbers we find. I know that I need the total in this row to be 49. If the total in that top row needs to be 49, I can go ahead and take 49 minus 27 to get my cell here, which is 22. Once again, I took 49 minus 27 to get that. Unfortunately, I can't use subtraction to fill in the rest of the table, so I have to go ahead and go back to my formula. For my formula, let's go ahead and look at this one next. If I want to find that, I'll go ahead and take row total, which is 89, multiply by my column total, which is 124, and divide by my overall 226. When I plug all that in, round into the nearest whole number, I'll get 49. Once I've gotten 49 there, I can go ahead and use subtraction to find 40 here, and use subtraction and addition to fill in the rest of my table as well. Now, the reason we fill in our expected values table as our first step is to go ahead and check and make sure we meet our 2 assumptions. That is, I need that whole 10% rule to be met, and what this is telling me is that in reality, 226 women is less than 10% of all the women who are victims of sexual assault. That is, I'm assuming that my population is really large compared to the 226 we surveyed. The next thing I need to do is make sure I'm meeting this 5 count requirement. And that is when I look at my expected cells here, all of these are over 5. Remember, we have some wiggle room here. That is, we can have 20% of our cells to be under 5. In this case, because I have 6 total cells, I could have 1 out of 6. And I could have 1 out of 6 because that's 0.1667 or 16.67%. It would be under the 20% requirement. However, it's better in this case. Once again, I'd like all my cells to be over 5. This is kind of just my tolerance down here. I've met the 10% rule. I have over 5 in each cell. I can go ahead and run a chi-squared on this. In this example, we're going to practice finding chi-squared for our second example. On the top here, I have my observed values. That is what actually happened. And on the bottom, I have my expected values, which I would do before I even started my test. Once I found all this information, the next thing to do is go ahead and calculate my chi-squared. When I calculate chi-squared, I'll organize it into a table. I'll list my observed values first, then my expected. After I list my observed and my expected, I'll go ahead and I'll subtract them. After I've subtracted them, the next step will be to go ahead and square those. And in the same step where I square them, I'll divide it by my expected. My step after that will be to go ahead and add these up. And that will give me my chi-squared. Now that we know the steps to go ahead and find our chi-squared value, let's work through the example. First thing I'm going to do is take my little table and I'm going to list all my observed values. I prefer to start at the upper left corner, so I'm going to start by writing 30 and then move across. So I'll do 30, then 19. I skipped the total. It's not one of the values I filled in. Go down to 44, 45 moving across, 50, and 38. This is my personal preference, and you don't have to do it that way. The only important thing to watch out is that however you trace across your observed is also you have to trace across your expected. So that is, I had 30, so when I fill in for my expected value, I'm going to put a 27 here, because it's in the same spot the 30 was. Same when I come up here with the 19, I'll put a 22 next to 19. I need to continue that way throughout my table. That is, match up my observed and my expected values. So a 49 here, a 40, 48, and 42. It's important to match them up, so I find the difference between, in that exact instant, my observed and my expected. So that is, I had 30 women who made over $60K a year and did not receive medical attention. I expected it to be 27. The difference between my actual and my expected is 3. Tracing it down the entire way, then, you're going to notice I get negatives and positives. And then, in fact, if I added all those up, I would get 0 out. And that's because these are the deviations from expectation. So, for instance, because 27 was 3 lower than 30, this 22's 3 above 19, and that's because they still have to add the same numbers. So if one went up by 3, the other one has to go down by 3, which is why, once again, I can't add these up as written. Instead, I have to square them to cancel out the fact that I could have negatives there. And if I'm squaring them to cancel out the fact that there's got to be negatives, I might as well go ahead and divide by the expected in the same step. When we do this, we'll keep 3 decimal places. So for this first one, 3 squared divided by 27, I should get 0.333. This would be a great opportunity to pause the video, fill in the table, come back and check. Now hopefully my values line up with your values. Once again, I'm keeping 3 decimal places in here. I have no negatives on here because I squared it. So if you're putting it into a calculator and get a negative out, make sure you put parentheses around it and then square it. Final step, I got to add all this up, and when I add them up, this will be chi-squared, which in our case is 2.06. So for our first full example here, we'll be looking at whether or not the site of injection for vaccine influences the likelihood of having a severe reaction in children. So is shot placement related to reactions or not? And when we go about doing this, what we need to do in the very beginning is once again, go ahead and find our expected values. To begin, I'm going to start by finding this expected value right here. Normally I'd start in the top left corner, but I already showed you how to find that one earlier. So to find this value right here, I take the row total, I multiply it by the column total, and I divide by the overall total. And when I get this, we'll go ahead and we'll round it to the nearest integer to make it straightforward. And I find this is 4,781. Now, in our previous example, we had to calculate more than one value this way. But in this example, because it is, once again, a 2 by 2 rows by 2 columns of data I need to fill in, once I find one, I can find all of the rest of them by doing subtraction. So take 4818, subtract 4781, and I'll find this number right here is 37. I can take 106 minus that number to get this number here, which is 69. And then I can take any of the other types of subtraction and go ahead and find this one, which should give me 8, 9, 2, 3. Now I've got all my expected values filled in. I go ahead and I check, and sure enough, all of them are over 5. And I'm going to assume that's more than 13,000. That's 10% of the overall number of kids who've been vaccinated. That is 13,000 is under 10% of all the children. So meeting the 10% requirement and over 5, I can go ahead and start my test. Now, I'm going to go ahead and calculate chi-squared in the very beginning so that I can erase it and make my test a little neater. And anytime I calculate chi-squared, I start by listing out my observed. My observed in this case are 30, 4788, 76, and 8916. And once again, I like to walk across rows. I don't include my totals because those aren't things I've calculated. My next will be to list my expected. When I list my expected value, I line up my cells. So where 30 was here, 37 is here, and so forth. 4781, 69, and 8923. The nice thing about a 2x2 like this is that when I go to take my observed minus expected, a lot of things are going to line up. For instance, you notice this is -7, and this is +7, and that's +7, and that's -7. And the reason why that's happening is when I moved 30 to 37, I increased it by 7, which meant that 76 had to fall by 7, so it still added to 106, and similarly, 4,788 had to fall to 4,781 to make it add. So wherever I say positive, the cell next to it has to be a negative. I've got this symmetry here, and once again, if I added those up, I would get 0 out, which is why I square them, and in the same step, I'll divide by my expected. In this case, going ahead and keeping 2 decimals, I'll get 1.32, 0.01, 0.71, and 0.01. Once again, that's like taking 7 squared divided by 37 for the first, or 7 squared divided by 4781 for the second. If you're ending up with negatives in there, you need to go ahead and make sure that you put -7 in parentheses, then square it, then divide by 37. My next step will be to add these up. When I add them up, I'm going to get 2.05, and this will be my chi-squared value. Now that I've got chi-squared, I'm ready to go ahead and perform my test. Now I've found my chi-squared value. Next step, go ahead and start my test. First, I'm going to list R, the number of rows, and C, the number of columns. In this case, I have 2 rows, and it's only 2 because I include thigh and arm. I don't care about my totals. That's not data. It's just what I get from summing up my data. Next, I list the number of columns, and there are 2 as well, yes and no. My degrees of freedom is R minus 1 times C minus 1, which will give me 2 minus 1, which is 1, times 1, or degrees of freedom 1. Next step, I'll go ahead and write down my hypothesis. My null hypothesis is I'm assuming these things are independent, and I have to assume that because that's how I calculate my expected values. So literally, I'm using independence as an assumption to calculate my expectation. HA is I'm going to try and prove they are dependent. Based on that, I went ahead and found step 3, which is chi-squared. Chi-squared is 2.05. And I'm going to use that in step 4 when I go to find my p-value on my chi-squared table. As a reminder, the chi-squared, just like a t-table, I start by finding my degrees of freedom row. My degrees of freedom in this case is 1, so this is the row I'll be dealing with. If my degrees of freedom wasn't here exactly, just like a t-table, I'd round down. Now that I've gotten that, I'm going to go ahead and try and find my chi-squared value on this table. My chi-squared value is 2.05. So I can find 1.64 and 2.07, and 2.05 would be in between those. That means when I trace these all to the top, my p-value would be in between those two. So that is my p-value is in between 0.2 and 0.15. Covering up the word p-value, I notice 0.2 is bigger than 0.15, so just like the t-table, as I move from left to right, my values are getting lower, so I'd put greater than symbols, moving left to right. Now I've found my p-value, let's go ahead and get rid of my table. And this takes us into step 5, which is my conclusion. To find my conclusion, I always compare my p-value to 0.05. In this case, I notice I have 0.2 or 20% and 0.15 or 15%. Well, I want to compare it to 5%, and 5% is definitely on the side of 15%. So if my p-value is bigger than 15%, my p-value is definitely bigger than 5%. Based on this, then, my conclusion is going to be that I failed to reject H0. That is, there's not actually enough evidence to say these are dependent. For all I know at this point, it turns out it looks like, injection site might have nothing to do with whether or not a child has a severe reaction.